Okay.
Yeah, okay, so it's my pleasure to introduce Jorge, Vitorio, Pereira, who will talk about effective integration of differential equations.
Thank you very much. Thank you for the invitation. Thank you for the opportunity to present some of my work. So I was unsure to exactly how technical it should be, so I prepared a talk which is not technical at all, and I will be glad to fill in technical details as requested, either during the talk or after the talk. So the general problem is that we have a polynomial differential equation, so it's a function of f(x), y prime, and we would like to determine algorithmically if all its solutions are algebraic or not. We are mainly interested in the case of ordinary differential equations, linear on y prime, so it's a first order of first degree, but not a linear differential equation. So I'm just saying that's degree 1 on y prime.
Question. So do you assume that f is over a field of constant?
F will be just a complex polynomial. Yeah.
And algebraic means
If they are algebraic
over C of x.
over C of x, exactly.
Thank you.
Excellent. Okay. And so I would like to start with the, as I will deal with the case first order and first degree, I would like to start with the history of the subject. And I think much of the activity was spurred by the work of Schwarz on this particular differential equation, on Gauss hypergeometric equation. So in this paper, he produced a complete list, right? And it's really one of these limit cases where it's not trivial at all, but it's still simple enough in order to be solvable. And after the work of Schwarz, where he determined completely the list of parameters, alpha, beta, there, for which we have algebraic, all solutions are algebraic, people start to look at the general problem. So let's just make some remarks why this case was simple enough to be solved by Schwarz, is that he was looking at a differential equation, linear differential equation of the Riemann sphere with three poles, and the monodromy representation is a representation of the Poincaré sphere, and all solutions are algebraic. Then all local monodromies are finite. This is the easy part, but somehow, as explained in this nice paper by Baldassare Dwork, he could do the other direction, so knowing the local information, he could somehow understand which cases led to finite monodromy representation, and this is the content of this passage. I not want to, probably already you know this much better than me, so I'm not insisting to it. But then there are a lot of activity on the problem follow in the course of subsequent years. Contributions by Fuchs, Jordan, Poincaré, Painlevé, Boulanger, Pepin, Frobenius, Haufen, and many others. In particular, this problem also will lead to great developments in the theory of linear algebraic groups. For instance, Jordan proved that n finite group of Gn has a median normal subgroup of index bounded by a computable function Tn. And in some sense, people were, after a lot of work, the people were convinced that the problem was solved. In the sense that they could produce, they could understand, given a linear differential equation, if all its solutions are algebraic or not. So we have this passage from the Klein's lectures on the icosahedron. Thus is the problem which we formulate at the beginning of this paragraph solved, and the problem is exactly a particular instance of the problem that I mentioned in the first slide. So at the end of the 19th century, the problem for linear differential equation was considered completely solved. So what's next? Then of course, there are a lot of external incentives to pursue this investigation. For instance, it was one of the attributions of Grand Prix des Sciences Mathématiques in 1881, perfectionner un point important la théorie d'équations différentielles du premier ordre et du premier degré. So, perfection, the theory of linear differential equations of first order and fourth degree, no longer linear. And so there are two memoirs which were we received prize for that, one by Pereira, another by Auton. And just after that, I think in 91, there is this paper by Henri Poincaré sur l'intégration algébrique des équations différentielles du premier ordre et du premier degré, where he essentially posed the problem that I've stated for the particular case of a function of x, y, y prime, linear on y prime, first order, first degree. And he started making a comment. So to know if a differential equation of first orders of first degree is algebraically integrable, which means all solutions algebraic, it's sufficient to bound the degree of the general solution. Because once you've done, if you have a priori bound for the degree of the general solution, then you could reduce the problem to to algebraic computations, and the problem was solved. And so he could do that. He could do that under very, very strong assumptions. So he looked at a differential equation, and for him a differential equation, a polynomial differential equation, gives rise to what we call today a foliation of the projective plane. He somehow compactified the space. And he imposed conditions on the nature of the singularities of the differential equation. So he assumed that all singularities of the differential equation are either of radial type, I mean that the vector field is locally x ddx plus y dy, and either they are what we call centers, kind of right. It does not look like a center because we are thinking over the complex field, but in the real field, this is essentially the same thing as this, right? And so he assumed that all solutions in this paper, he assumed that all solutions, all singularities of your equation were of that particular kind with that first, with that linear term. And he succeeded in providing a bound for the degree of the differential of the general solution, the degree of the first integral. He built his result using the theorems by Darboux and Haufen, which I will not enter in detail exactly how he does that, but of course I can explain to any of you afterwards if you want to. So.
What is the bound?
It's not really. You have to write down that you take m is the degree of the equation. You have to and p is the degree of the general solution, I think, and he writes something like that, and then you see that p must divide m plus 2, and it's not a bound is not a given bound, but
procedure to find it.
The procedure to find the bound is not that hard.
But in terms of only of degree of the equation.
Of the equation, but under that extremely strong assumptions.
Mm-hmm.
And somehow this problem was revisited in the 90s in a paper by Cerveau and Misneto.
Oh, and if one, so maybe his bound is quite sharp. But if one relaxes that, like if one doesn't want to get a really great bound, can one simplify it and give it just in terms of the degree, not as a procedure, but like
yeah, you
degree?
can.
Is it more than degree? Is it degree squared? How does it approximate?
It's a problem. I think it's linear on the degree.
It's linear on the degree. Okay.
Okay, and so. Somehow in the modern literature of filiation theory, the Poincaré problem which I like to understand as, does there exist a procedure to decide if a given differential equation is algebraically integrable or not, became, well, let's bound the degree of the general leaf. Let's bound the degree of the general solution. In function of what? Well, in function of the degree of the equation, the degree of the coefficients of the equation, and also combinatorial data attached to the singularities. Because of course, if we don't do that, simple example like px ddx plus qy dy, so have degree 1, but if you look for the first integral, will be something of the form x to the p over y to the q, and something like that. And the degree will not be bound. And there are positive results. A lot of activity was done in this, so you assume that the curve is smooth or has at most nodal singularities, then you do have a bound. If you assume that your foliation has no dicritical singularities, which are like the base points of a pencil, you also have positive results. You have positive results for more generally for curves with bounded singularities, meaning that the singularity is not too bad. So we have bounds in positive characteristics, higher dimensions, higher codimension, and many more. But one thing that either you are assuming all these results, either you're assuming that you already know that the singularities of your curve are not that bad, or you are assuming that the singularities of the foliation are not that bad. But it's unreasonable. If you want to decide if a given differential, the differential equations is algebraically integrable always have dicritical singularities. So even in the assumption of some of these results is saying already, well, let's assume that we do not have a rational first integral and let's try to do something. But anyway.
So, but may I ask, when you refer to the curve, you mean generic algebraic solution?
One algebraic solution.
So like the points without fundamental curve says that if for some reason I know that algebraic
saying
solution...
that, well, the degree of nodal curves invariant by a foliation of degree d is at most d plus 2.
So if I don't find any invariant curve, I'm interested in finding nodal curves, then I'm good.
Yes.
Okay, I see. Thank you.
Okay. But there is a negative result by Lins Neto himself in the early 2000s. So there exists a one-parameter family of foliations of fixed degree, so a one-parameter family of polynomial vector fields of fixed degree, and fixed analytical type of singularities. Not only the combinatorial data is fixed, but even the local analytical type is fixed, such that for a dense set of parameters, the foliations are by algebraic leaves, every leaf is algebraic, and the degree of the algebraic leaves is unbounded. So if you want to interpret the Poincaré problem in that sense, the answer is no, but that's not the original question. So here, this example is, it's not very complicated. As a matter of fact, a while after this example appeared, we realized, McQuillan realized that it's defined by the quotient of linear flows on abelian surfaces. Adolphe Guillot also gives some very explicit explanation of this phenomenon. So here's a situation where there is no singularities, and when you take a quotient by a finite group, you can end up with something birational to P2, and that's the case. That's what Lins Neto found explicitly. Okay, but let me go back to the linear case, right? The results that I mentioned of the 19th century did not actually solve the problem. What they did was to reduce the problem to dimension 1. They showed that in order to decide if all solutions of a linear differential equation are algebraic, it suffices to be able to decide if the solutions of rank 1 algebraic differential equations are algebraic. But the catch here is that this A of x is no longer in Cx. It's no longer on the function field of P1, but it's on the function field of compact Riemann surface. And it's funny because if you look at this book by Hardy, there is one passage where he looks exactly at this kind of problem. And he ends up mentioning something, but no method has been devised as yet by which we can always determine a finite number of steps whether a given elliptic integral is pseudo-elliptic and integrated if it is. And there is reason to suppose that no such method can be given. So in modern language, this problem, reduced to the problem to decide if holomorphic connection on a line bundle over algebraic curves has all its flat sections algebraic. And in order to solve it, we can see that what we need to do is to provide an a priori bound to order of degree 0 divisor on algebraic curve. So somehow from the connection we produce this degree 0 divisor. It's an element of the pk group of the curve, and we want to know its order, give an a priori bound for the order of it. And I guess for an analyst, this seems kind of an impossible problem. It's a problem which you cannot, I don't see how to do it numerically, but it was solved by Hisch, and he did, what he did is to how to algorithmically decide whether the solutions of y prime ax y are algebraic by considering reduced to positive characteristics of the equations involved. So reduction to positive characteristic of this degree 0 divisor, and then positive characteristic in over finite field, degree 0 divisors have finite orders, so he do two different reductions, get two finite orders, take the least common multiple, it's a priori bounding characteristic 0, and then you can solve the problem. And it's related to a conjecture, all this is related to a conjecture of Grothendieck-Katz, which predicts how linear differential equations, how the solutions of linear differential equation characteristic 0 behave when reduced mod b, but I don't want to get much into it. But somehow this, what we can see from this classical, the history of this problem for this differential equation, there was one geometric component, which was the work from the 19th century, which succeeded to reduce to the rank 1 case. And in rank 1 case, it was unavoidable, we had to use arithmetic. So I want to somehow, I don't have definitive results on the subject, but I would like to propose an approach to the problem for polynomial differential equations, which somehow mimics the linear differential equation history. So I first would like to find one reduction using geometry, and then once we had this reduction, we could try to do something based on the arithmetic, like for linear differential equation. And so the reduction that I propose is essentially contained in this conjecture. So let's now just take all polynomial vector fields of a given degree. So that's what being represented by this projectivization of cohomology group. So these are all polynomial differential equations, all foliations of degree d on P2. And I want to look inside of this space. It's a finite dimensional projective space. I want to look all foliations which have rational first integral. And I would like to understand its Zariski closure. Because if you understand its Zariski closure, if you could at least dream that we could produce equations for the Zariski closure of this set, and then you could check if they are in there, and hopefully the fact that for a Zariski dense set we have rational first integrals would imply some stronger structure, or some structure on this foliation. And the structure which I predict is that these foliations are transversally projective. So what is that? So probably you're already familiar with this concept, but in another language. So we start, if you have started with a vector field, from the point of view of differential algebra, perhaps the simplest of them are the ones which admit a rational first integral. Then you can go on and just allow Liouvillean first integrals, where you add the exponential of closed-bound forms and things like that. And you could go on one step further and allow something some people call Riccati extensions or transversally projective foliation. So you allow now to put in your set of functions not only primitive of an exponential of primitives of closure differential form, but you also allow to solve linear differential equations. So that's
Of any order.
of any order, but it reduced to order 2. In the definition, we use only order 2. So we are allowed to put solutions of Hikachi equations there. Okay, so we have this hierarchy, algebraically integrable, rational first integrals, transversally Euclidean, given by a closed rational one form, transversally affine, which is kind of an extension of the concept of transversally Euclidean, which is exactly Liouvillean first integrals, and this more general case of transversally projective foliations. Okay, so this fact that transversally affine and the existence of a first integral on a Liouvillean extension is a theorem of Michael Singer. It's the characterization of vector fields which admit thing. And transversally projective, existence of first integral on a Picard-Vessieux extension. Okay. Very good. And again, much of, as is clear from this, all this is kind of, it's a conjecture, it's somehow based in history. So this is a passage from Stockholm Lessons by Pereira, where he says that we should not try to decide in one coup, in just one iteration, the problem if a given algebraic differential equation has all solutions algebraic, but instead you should first try to reduce it to an equation integrable by quadratures, whatever that means, and then study when a foliation given by quadratures admits all solutions are algebraic. And so this is somehow my interpretation of this thing. So this conjecture which I made joint with Roberto Svaldi. Okay. So let me discuss, I will now discuss two sets of results. So the first one is, you can, in the beginning I was interested in foliations where all solutions are algebraic, but I can also be interested in foliations which admit not only a rational first integral, but a Liouvillean first integral. And so what can we say in that case? So we have positive results in this direction under rather strange assumptions. So it's a joint work with Gael Cousin, Lins Neto, Alcides Lins Neto, and we can prove the following. So the first result is the following. So we start with foliation of degree D on the projective plane, and we assume that the foliation admits a Liouvillean first integral. But it does not admit a rational first integral. So we assume from the beginning that it's not algebraically integrable, something that we cannot check. That's what I'm kind of unhappy with this result. But then we can prove that we have an invariant algebraic curve of very, very small degree. Degree at most 12, D minus 1. And indeed, I have not stated, and I didn't put it into the slide, we can go even further. We can show that there is a decision procedure. We can produce bounds, which now will depend on the combinatorial data of the singularities, the degree of the foliation, everything, which will give a bound for the, not only for some algebraic curve, but for the whole integrating factor. Okay? And so how we managed to prove this thing? So this result is a consequence of a structural result for transversely affine foliations, which I proved previously with Gael Cousin, which essentially says the following. Let's see if I stated here. No. Yeah, I somehow state. It says that if I give you transversely affine foliations, we are in one of the two situations. Either it's the pullback of a Riccati foliation under a rational map, or it's a quotient of a foliation defined by a closed rational one form under a finite cyclic group.
I'm just wondering, so this is, so if you vector field, okay, so it's, okay, P2.
But you can think on a fine vector field. So
Yeah. Is this really saying? Okay, so suppose we rephrase it just. So if leaving first integral, say. Okay, I'll ask later. I need to think a little more.
okay, so let me go back. So what I prove is that in this result with Cousin is that if your foliation admits a Liouvillean first integral, it can be of two flavors. Either it's a rational pullback of a Riccati foliation, or it's a finite cyclic quotient of a foliation defined by closed one forms. So, in the case to the right, it will be a pullback. We are on a rational surface. It will be a pullback of a foliation on a rational surface. We didn't leave the word of rational surface. But on the left, this foliation, which we are taking the quotient, can live on a surface which is more complicated than a rational surface. It can be with a surface where we have holomorphic one forms, like an abelian surface in the example of Linz-Neto, and we don't have a priori any control on the kind of surface that we get. And so what we do we solve the problem using ideas from birational geometry. In both situations, we have to work differently. And in the case where we end up in a cyclic quotient of a closed rational forms, the main idea, let me just explain the main idea. In the case where there is no covering at all, the idea is the following. So you know a priori that you have, you're on a P2, it's a simply connected variety. To have a Liouvillean first integrals implies that you actually have an integrating factor, you actually have invariant algebraic curves. Otherwise, you would have a rational first integral. So somehow from this, you have this set of algebraic curves, which on P2 could be very singular. But somehow, using the fact that you have a Liouvillean first integral, you can prove that in this set of invariant algebraic curves which support the divisor, which support the invariant divisor, you can find, which support the integrating factor, you can find a divisor which is numerically equivalent to 0. And since we are on P2, numerically equivalent to 0, as soon as these guys are integral, it's the same thing as linear equivalent to 0. Since we are on P2. So here I have a rational function, right? And by assumption, our foliation does not have a rational first integral. And now the idea is to compare the level sets of this rational function with the level sets of our foliation. So here what you do, you resolve the indeterminacies of this thing. So this will be the...
May I ask, so what do you know about this rational function? So
I know that the zero set and the infinite set
are invariant.
Are invariant.
But you don't know that it's like first integral or something, right? So
it's not.
Okay.
I know that it's not. That's where I'm using the assumption.
Yes, yeah. Okay.
I know that it's not.
So you know only for zero and infinity set, but not about other level sets.
Exactly.
I see.
And so, if this thing has the degree, the small degree, we already have this theorem. So you can assume that this thing has every component that has degree very large. Mm-hmm. And so when you compare this foliation with your foliation, original foliation we are studying, we are going to see that some set will appear here. So this will be some invariant by f. that's the only way to have these poles of these invariant curves of very high degree, because you have some other curves with some other degree which are invariant by f. And they will also be, since they are compact and they do not intersect these pieces, they will be also be invariant by the foliation, the fibration, this algebraically integrable foliation which we produce here. And so computing the degree of tangency between these two foliations, that we are going to find the degree, the bound for this degree of these curves. Okay, so that's essentially the idea. But then, this is when you can argue on P2. So there is no cyclic covering involved. And to do the reduction from the general case, we need something more. We need this kind of, I think it's a nice elementary result, which somehow we had to prove it using modern proof techniques, meaning math over flow. And it says the following. So let be a subset phi of primitive roots of the unity. And let assume that all primitive roots of unity is the disjoint union of phi and phi inverse. Then for some n of order at most 6, 1 can be is in that set. So that's somehow explained the 12 there. The 12 comes from this.
And is it 6 sharp?
Yes.
Okay. May I ask again about this picture? So, but were 0 and infinity sets also invariant by f?
They are invariant by f.
And why do you prefer the middle one?
The point is that I don't have a priori. I have no control on the degree of these guys.
Yes.
And they could be either they have small degree and I'm happy and then I stop.
Mm-hmm.
If the degree is very large, I know that there will be something more invariant by f.
Okay, but it also might have large degree, right?
But what I prove computing this, because the degree of this foliation, let's call this foliation A, which is algebraically integrable, is essentially the degree of these guys. And when I compute the tangency of two foliations, what you do is you add the degrees. But since this thing is already on the tangents of the two, so then I take it out, and so this will have degree small.
I see. Okay. Okay, yeah, thank you.
Okay. And in the other case, the case of the foliations, a rational pullback of Riccati foliations, we have to do some birational geometry. So this is the case where this foliation we have a classification of foliations in terms of their Kodaira dimension. It's the growth of the number of sections of its pluricanonical bundle. The canonical bundle is the bundle of one forms along the leaves of the foliation, and we have to effectively control that. We can prove this other case. I don't want to say too much. I will say a bit more in the.
So I have a question about theorem A. So you started with discussing linear differential equations for which all solutions are algebraic.
Mm-hmm.
But now you have a second order differential equation, right? And you're talking about a relation between.
No, it's first order. It's first order.
It's first order.
First order. It's a vector field.
Well, okay, so dimension. Okay, so it's a second order differential equation.
Hmm?
So you have two coordinates.
Yes.
And when you're talking about having first integrals, you're talking about relations among the coordinates, right?
Yes.
So it's no longer saying that each coordinate is algebraic, or each coordinate satisfies the property. It's talking about relations.
Yes.
So it's a kind of different flavor question, right? So the original question was talking about, say, if you know.
No, but here it's also the same. You can think of these equations as something like this. So it's properties of solutions. So we want to know if the solutions are algebraic. If you write like this.
So you consider of two coordinates, you consider one to be a function of the other.
Ah, okay.
If you want, you can do that.
Ah, and that thing has constant coefficients. That's what. Okay.
Constant coefficients? What do you mean?
Like there is no t there, so like.
No, there's no t.
Okay.
So this is dy dx.
Mm-hmm.
The prime is.
Oh, got it.
So it's, I think it's the same.
So it's the same. Yeah.
It's the same.
It's
You just leave. You just left the linear word. Now you no longer assume that your equation is linear. Yeah, but somehow this is strange. I agree with you. I'm just putting a result where I was all the time discussing the algebraic solution, and now I'm assuming that I have none. But somehow it fits into this hierarchy of integrability, and I want to understand how to relate one to the other. And so, but you're right that it's perhaps not the most natural choice of statement to give just after the whole discourse. So this one is perhaps closer to this discourse. So now, something that already Poincaré proposed, and Poincaré looked at that. Now we can somehow the general problem for a general algebraic solution is too hard. So let's look at a particular case. So now let's just fix a G, a genus, and let's ask if we can decide if your differential equation has all its solution algebraic of genus at most G. And so this somehow is a positive result in that direction. So suppose now that my foliation is algebraically integrable, right? But I also assume that it's a family of genus G curves, and I will also assume that this family is non-isotrivial. Two general members are not analytically equivalent, okay? And in that case, I can give a bound. A ridiculous, horrible bound, but it's a bound, right? 7 times 42 times 2g minus u factorial. If you're not happy with that, you take the square and multiply by degree of f, and it works. Okay? And so how we prove that? So this is a joint work with Roberto Svaldi. So this the idea here is to explore. There is a very simple observation. The problem of deciding if all solutions are algebraic or not is obviously a birational invariant problem. If you change the birational model of your foliation, it's still, if all solutions are algebraic, they will still be algebraic. If they all have genus G, they will still have genus G. So you can try to look for birational methods to prove that. And so what we did is that we realized that for a foliation we have, for a variety, when you do birational geometry, you are somehow forced to look at one line bundle, right? And its powers, the canonical bundle of the variety, the bundle of top dimensional forms for the variety. For the foliation, you have two natural bundles. You have the canonical bundle, which are one forms along the leaves, and you have the conormal bundle, which are one forms which vanish along the leaves. And now we look at combinations of these two bundles and produce the rational invariance for the foliation. And somehow we can compare this for the foliation to the birational invariance when we restrict to the curve. So one will become the normal bundle of the curve, since we have in the situation of rational first integrals after resolving determinacies, the normal bundle of the foliation along the invariant curve will be trivial, and the other will be the bundle of one forms, which you can study with him and Hock, right? And so we have to produce methods to produce lots of sections of this guy, the big guy. So these assumptions where it's not equivalent to a isotrivial fibration guarantees that I can produce something like lots of sections, taking powers, and it will grow quadratically with the power that I'm taking. And when I restrict to the curve, it grows at most linearly by Riemann-Roch. So eventually, you're going to have a section which vanishes along that curve. And so we produce a section on something birationally equivalent to P2. When you go down to P2 to produce a polynomial which vanishes along the curve. So that's how we do that. And that's the kind of techniques that we have to use. So this is the techniques to produce sections This is this work of Zariski. So this is the effective non-vanishing of the joint linear series. The Zariski decomposition of the canonical bundle, which is the one that describes the structure of the canonical bundle of the foliation. And the work that we have to do by ourselves, this is in the case of this genus G fibration, to bound the multiplicity of components that we had to and we put all this together and we were able to prove this kind of result. So this technique is very close to birational geometry, and also with something that people in Diophantine approximation do a lot, right? Produce polynomials vanishing with that.
But what's hyperbolic foliation?
Hyperbolic fibration. So
Oh,
this is fibrations of genus at least 2.
Ah, I see.
So here the problem is that we know that the general fiber is reducible, but you could degenerate to something which has multiple components, and these multiplicities are very important to control everything. So these multiplicities are essentially responsible for this factorial there. Because these are the denominators will appear in the Zariski decomposition, and to apply the result to produce series, you have to kill denominators, and that for 42 2g minus 2 is the thing that is kind of the bound for the multiplicity of components.
Okay.
The 7 come from this business of effective non-vanishing. But yeah, so the idea is just that somehow all this, you're going to have 2 types of components. You have the components which are still hyperbolic, and the ones which are not. You have to show that these which are not you can get rid of them in a good model, in a good operational model, and the others which are hyperbolic, we always contribute with something positive to a certain volume, and this positiveness is 1/42, like proof of bound of automorphism group of genus G curve, and so. Anyway, that's what we have to do. And with that result, we can prove this. So it somehow points in the direction of the conjecture. So the Zariski closure of the set of degree D foliations admitting a rational first integral with general fiber of genus at most G is formed by transversally projective foliations. It's exactly the cover.
This for every G, right? So
for every G. But I have to bound G.
yeah, okay.
And so this is done using the classification in terms of the codaric dimension, and we introduce another invariant which we call the adjoint dimension, which behaves much better than the codaric dimension in families, because that's our problem, it's a problem about families. And doing Noetherian induction and using theorem A, we can prove this result. Okay? So let me just review briefly this classification. So you see the classification according to this adjoint dimension and the codaric dimension goes something like that. The things which have adjoint dimension minus infinities are either rational fibrations, fibration of genus G, or a finite quotient of a foliation generated by a global vector field, or a recursive foliations. Adjoint dimension 0 is a finite quotient of a linear foliation on torus. Adjoint dimension 1 is a finite quotient of E times C to C, where genus of C is at most 2. So the base is hyperbolic and the fiber is elliptic. Or is a finite quotient of the same thing but the other way around, E times C to E. So now the fiber has genus at least 2 and the base is elliptic. It's a turbulent foliation, a foliation which is transverse to fibration by elliptic curves, or it's a non-isotrivial elliptic fibration. This is the adjoint dimension 1. And adjoint dimension 2, it's the rest, reducible quotients of times h to h, finite quotients of C1 times C2, where both curves have genus at least 2, or it's just the foliation of general type in the usual series. So this is really, it's not hard, it's really the hard thing. We use this deep theorem by McQuillan and Brunella and Mendes, which is the classification of foliations in terms of the quadratic dimension. But as I said, for the problem that we have at hand, this adjoint dimension behaves much better and behaves much better in family, and also seems to be more appropriate to look to this kind of questions. And I think that's all I had to say. Sorry if I was too fast, but as I said, I prefer to discuss now any particular topic or any particular give any details of any of the arguments than to just present lots and lots of definitions.
So this next speaker. I have a question about the conjecture. So could you explain again why do you think proving this conjecture?
So what's the? Could you show the conjecture?
Yeah. So can you go to the conjecture back?
Sure.
Yeah. So like as you prove this, so what would be the next step towards the Poincaré problem? So if you know that this is true.
If it is true, it's solved. Because we have another result, that transversely projected foliations.
Mm-hmm.
This is a result that I have with Jorge and Touzé. And we have proved that if you have a transversely projected foliations, you have also two possibilities. Three possibilities. They are either transversely affine, which are already described by the result with Cousin. They are pullbacks of recursive foliations, right? Or they are something that we call in the subject Hilbert modular foliations. So the Hilbert modular foliations, you can check algorithmically that they do not have rational first integrals. Even if you have a foliation, it does not. And Riccati foliations are what? Riccati foliations are projectivizations of second order differential equations. So this reduced, if we know to prove this, this reduced to the case of linear differential equation, essentially. Morally, let's say. Of course, all these, in all times that when I say there exists the foliations are pulled back by a rational map of a Riccati foliation, we would still, if you want to really implement this thing, we would still need to find this Riccati equation and find this rational map. But I know a priori that they exist. So we can find them. I'm not saying that I'm giving an algorithm to do.
Mm-hmm. So, but like, okay, so if this conjecture is settled, then the way answering Poincaré problem would be first to check whether we have transversely projective foliation.
Exactly.
And then we have one of three cases, and in each of these three cases we
have methods to deal with
have
that.
some methods.
Yeah. Oh, and also I'm saying I should not be so optimistic, right? Yeah. I think that this settles the case, because saying that the Zariski closure is transversely projective is somehow saying that we have this set of equations on the coefficients of the differential equations satisfied by transversely projective foliations which are on the closure, blah, blah, blah. Mm-hmm. But it's unclear how to produce this set of equations, right?
But do you know for some reason that transversely projective foliations actually form algebraic variety?
For me, it's unclear. Perhaps
so the conjecture also assumes this, right?
No, this is a strong conjecture. This is a strong version. This is a weaker. I'm just saying, all foliations have rational first integrals, take the closure of the Zariski closure of them, and I'm saying that this is contained the set of.
But transversely projective foliations might be more.
Might be more.
So consists. Okay, consists. That was confusing. The consists. Is that what?
Yeah, so I thought like this is exactly all fine, but it's contained. It's contained.
It's contained.
One question that you can ask, Yeah, it's contained in the set of transversal, which I don't know it's closed or not. I believe it's closed also,
Okay.
but this is some kind of weaker statement. And one thing that you could ask is, well, can't we hope that the Zariski closure is transversally affine or transversally Euclidean, right? Because we have, and no,
So there are like
there are examples. It's very similar problem. If you look at the problem that you probably know better than me, so you look at all linear differential equations of second order over P1 with, I don't know, 4 points. You look for those for which the monodromy is finite. This, if you take, this is a Zariski dense, right? And so you start with the closure of this guy, you go to the full linear group.
I see.
So if you look at representations with finite image and you take the Zariski closure of that, you end up with the whole representation space.
Thank you. Other questions? Okay, then let's thanks again.